probability to the meta level from probabilistic programs to probabilistic properties of programs. And it's presented by Mingzhang Huang.
Yeah, thank you. Thank you, everyone. And today I will introduce our work about the modular verification for almost sure termination of the probabilistic programs. It's a joint work with these guys. First, I want to say in our setting, the probabilistic programs are the classical programs, such like the imperative programs, extend them with some random value generators, which generates some random values according to some given or desired probability distribution. And under this setting, we consider about the termination problem. The termination problem of the non-probabilistic programs are very famous. It's just like about something, the Turing machine. Yes, and in the probabilistic world, it asks whether the program terminates with the probability 1. Let's start with some examples. This is a very simple while loop, and it is not the complete program since we haven't given the distribution of the random variable r. The x is the program variable and r is the sampling variable. Let's consider the almost sure termination, and when r equals to have the probability 2/3 with r equals to -1 and the rest is r equals to 1, then the programs intuitively terminates since the value of x decrease in expectation. And if we use another distribution, like it's showed in the slides, then intuitively the value of x increases for every step. So it doesn't terminates, almost sure terminates. And when the probability is half-half, it's just like a random walk. And as we all know, the random walk of x this time it will stops. And it will go to every single point and with probability 1. So it terminates with probability 1. So it also terminates. Termination problem is the most basic and the fundamental notion of the liveness of the programs. And it is famous too for its undecidability for general programs. Since according to the recursion theory it's just basically is the halting problem, and but in non-probabilistic programs, the undecidability is aroused by the recursion, and the above 3 examples reveals that even the value of the program variable doesn't affect the control flow of the program. It still may change the answer of the termination problem. And we now focuses on the programs just in a very simple syntax and a very simple form, and study how the distribution influences the termination probability. And yeah, that's what I say. This is not since the general problem is not is undecidable, so we only can find some method is sound, and which is not complete approaches. For the classical methods, for the non-probabilistic program, we usually find some ranking functions for the program. And to the probabilistic program, we usually find a ranking super martingales to the program. Informally, a ranking function decreases for every step, and the program terminates if the value of the function is negative or below than is small enough. Similarly, a ranking supermartingale decreases in expectation of the value of the function for every step, and it also if the program terminates and the value of the function or the value of the supermartingale is negative or small enough. This is the concrete definition, but I should ignore it here. And I just want to show you by some example, by a simple example. In this case, and we can set this is a probabilistic program, and we set the ranking function, not ranking function. The ranking supermartingale is just the x. Maybe I should write it into a big X, but it's for some reason I write it in small x. And we just focus on the value of x. So we know that in expectation for every step, this function or this random variable decreases. So which concludes that this program almost sure terminates. Now we start with some modular verification. Since this section is all about modular verification, so I won't say too much about the motivation of it. And for the traditional way, there is a rule in a whole logic rule, something like that, in this form, to deal with the modular verification. It says that if for every sub-program PK, if every sub-program PK terminates, and we can find, if we can find this R means some ranking function, find some R decreases for every PK, and at least there exists someone decreases strictly, then we conclude that the whole program terminates. It's very intuitive, and it also is sound for the non-probabilistic programs. And in this paper, this paper claims that this rule is just the same formal rule is sound for the probabilistic programs, and we found that there's some problem in this rule. Let's we write this counterexample for the rule. Maybe it's too small, but I can explain it for you. This program is a nested loop. There is an outer loop and an inner loop. Basically, the inner loop is just a random walk. If the R is the sampling variable R is fair, have half chance to -1 and half chance to be 1, then we can say that the inner loop is just a fair random walk with a barrier at location 2, because if x is smaller than 2, it will just skip and don't do anything. And the whole steps of the random walk is z, and there are 3 program values, variables x, y, z in this program. The inner loop says that there is a random walk with barrier, and the outer loop runs this random walk for many times. Actually, the steps of the random walks is y, and the y increases exponentially for every outer slope. So let's Moreover, this example, this program terminates. Well, let's see if x is equals 2 for after execution of the inner loop, then x will be assigned to 1 by the line 9, and 1, 2, 1, 2, and it will if for every execution of the inner loop x is assigned about to 2, then this whole program will not terminate, and it's if and only if. So we calculate. We want to calculate the for every inner loop the x value is 2. This is just a graph to illustrate the inner loop, and the beginning point is 1, and assume that we have y steps, and assume that we have for the random walk, for a path of random walk, there are m minus ones. We want to calculate how many paths contains m minus ones and avoid to hit the barrier. This is a famous result called Catalan number. Is in this form, and we calculate the probability that the x equals 2, and this is a result. For the Catalan number, the term of Catalan number is just the numbers of the paths. The number of paths that contains m many minus ones, such that did not hit the barrier 2, and we add them up to have the whole number of how many these paths are, and get the result. After that, for Stirling's approximation, we found that this property is no smaller than 1 minus e over pi in the square root of y for every even y. It looks very simple, but in a very simple form. And this is for every inner loop. Now we consider about the outer loop. The first term is said that it is the terminating time is infinite. Infinite time of the terminating time is just for every inner loop, the x is assigned to be 2, and we product and everything is independent. We just can product them together, and we find that for the former inequality, the result is just the production of that. This infinite production converges to a non-zero number if and only if the infinite summation of qi converges, and we can say that we can find that it converges for the d over 2i. So we have proved that this counterexample is not almost sure terminating, but let's go back to the program. For the V rule, you can say for every step, for every sub program, we set the x to be the ranking supermartingale. Then for the second, for the inner loop, it is a supermartingale since it's a fair random walk, so the expectation doesn't increase, and for every step the condition holds, and there is a line 9 x x is assigned to be the x minus 1, and this makes the whole make the super martingale decrease strictly. So this program satisfies this condition, and it will conclude that the whole program terminates, almost terminates. So this is we proved that this rule is not sound for the probabilistic program, and we found that the crucial flaw in the rule is that the non-negativity of the ranking super martingale. In the inner loop, the value of x can be infinite, minus infinite, any large for any large, and we want that if x is smaller than some number, or if x is negative, then the program stops. It halts, but it doesn't. So it's the crucial flaw of it. So now we want to say something about our approach. We suggest the previous approach with strict decreased condition at every statement, not for if there exists one. And the negativity is then resolved through concentration equalities, which guarantees that the probability of a value of R tending unbounded to minus infinite is exponentially decreasing, so that we allow that our super martingale to be negative, but the probability can be bounded, exponential bound. So we use this DSM, so-called DSM maps. It's decent super martingales which are not restricted to be non-negative and are sound for proving almost sure termination of probabilistic programs. After that, we developed some template-based algorithm for synthesized DSM maps. If we set the linear templates for synthesizing, then we have the polynomial time results of it. It uses Fox's lemma, and the solution can be found through linear programming. And this is an example for our approach. You can say it is a very complex program, and we can find the ranking super martingale for it. Let me give you a conclusion. We give the non-trivial counterexample for previous modular approach, and we give a sound modular approach. And based on this, we develop some algorithmic methods. Yes, for future work, we can consider more general programs and about the recursions. Thank you. That's all.
Thank you. Any questions from the audience? If you need time to think, do I have to feel bad that I don't know what a super martingale is? Or who, maybe?
Oh, since super martingale is, yes, super martingale is some, how to explain it? It's just like the second paragraph of it. It's intuitively, it decreases for in expectation of the random variables, just like the last one, the last condition is that.
Is it named after a person or after a storm? Or what?
Yeah, I don't know.
Any real questions from the audience? Yes.
Hi, thanks for the talk. Have you any idea how easy it is, given an intended probabilistic program, to come up with such a super martingale that decreases at every statement?
We write it into the condition of our DSM maps. That's it requires that every so just like the example. I want to say that. These ranking supermartingales decreases for every step, but we do not have a global supermartingale. We assigned every expression to every single label as a parameter, so we can find that this works. Okay.
Okay, thanks.
Sophia, you had a question?
So you have shown how difficult it is to reason about termination in probabilistic programs. Yes. I was wondering about reasoning about the properties of probabilistic programs. Is it something like functional properties? Is that something you want to tackle? And in particular, I thought probabilistic programs are kind of their own specifications. So have you got some particular examples in mind? So two questions.
To calculate the probability of its probability is very hard to implementation, since the condition is very complex. So we are going to consider about the programs about finite terminations. That's such that the terminating time is finite, but we cannot deal with the probability of it. We only give it give the upper bound and the lower bound of it, of the probability of it terminates or the terminating time. Okay, thank you.
Thank you.